This is the second part of the unit, AS unit, amount of substance. The first part was the skills that you needed. Now we're moving on to the content of the unit. So we're going to start with relative atomic mass and relative molecular mass. This is different definitions just to make sure they can differentiate between those ideas. So please pause and try to come up with what is the definition for the term relative atomic mass of an element. So these are the answers based on the exam questions from AQA. This would be the same for GCSE more or less. So you can see there are 2 marks, and in each case you need to have 1 mark for the top line and 1 mark for the bottom line. So you could write it's an average mass of an atom divided by 1/12 mass of 1 atom of carbon-12, right? If that's what you would prefer to do. So for example, I could choose an average mass of 1 atom of an element divided by 1/12 mass of 1 atom of carbon-12, right? There's other options in there, so read and choose which option works best for you, and you can try to memorize it, make sure that you know it for 2 marks. So you also should know how to calculate relative atomic mass. This was explained in the unit atomic structure and also in your GCSEs. This is a reminder of how to calculate it if you just need to refresh. Now, so this is if you have information about the isotopes. Now, what about relative molecular mass? So can you pause and have a go to give us a definition? So this is what you have as a definition that you get a mark for in the exam. So it's average masses of atoms in formula divided by 1/12 mass of 1 atom of carbon-12. Or the second option, average mass of 1 molecule divided by 1/12 mass of an atom of carbon-12. Now, why is the average? Because atoms within the molecule that we're talking about in here, they may have different isotopes. Okay, so that's why the average, because that averages all different isotopes. Now, the term relative formula mass will be used if we're talking about ionic compounds. That's why we don't normally say relative molecular mass. I often just say relative formula mass for everything. Now, the symbol MR is the same, but you just need to remember that if it's ionic compound, it's not called relative molecular mass, it's called relative formula mass. Yeah, so that's something for you to remember. What about relative isotopic mass? So it's an average mass of an atom of an isotope compared to carbon-12 in the same way as in the previous definitions. So you're looking for an isotope, yeah, and you could have it like so. Right, so we're going to look at our old friend, the mole, and the Avogadro constant. If you want to run a chemical reaction, how do we know how much of each reagent to use? What do you think? Well, our chemical reaction of a chemical equation of a chemical reaction, that can give us some sort of information there, right? It tells us 1 carbon atom with 1 oxygen molecule gives me 1 molecule of carbon dioxide. Unfortunately, atoms of different elements, they've got different masses. So the equation tells us how many atoms we need, but not how many grams. In reality, in the lab, we need to have the quantities. You know, you can't count single atoms or molecules. You can't say 1 carbon, 2 carbons, 3 carbons. We need to be able to weigh out, measure out. You can measure the volume, or we can measure the mass, but we can't count single atoms or molecules. So to be able to change from the information that the equation tells us, which is 1 atom of this plus 1 molecule of that, from this kind of information to a macro scale, so to a large scale, to a scale where we can handle these quantities, we need a mole. So mole tells us how to translate information from the molecular level to a level that we can handle. So what is a mole? Have a little look and enjoy. Credit to
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your ant's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amedeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists look at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Unfortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is... anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
So 1 mole of a substance contains 6.02 times 10 to the 23rd particles. That's called Avogadro constant. And you can think of it as a dozen, but a much, much, much bigger number because it always contains the same number of particles. So depending on the size of the particles, the mass of 1 mole of something can change, can be bigger or smaller depending how big the particles were. However, it will always be the same number of particles. And mole is the English version of that German word coming from molecular weight. So some more examples, like they gave us in the video. One more of standard soft drink cans can cover the surface of the Earth to a depth of over 200 miles. And if you have a mole of unpopped popcorn, the US would be covered in popcorn to a depth of over 9 miles. And if you were to count atoms at the rate of 10 million per second, it would take about 2 billion years to count the atoms in one mole. So, you know, it's huge number. So how is it helpful to us? Well, carbon atom has 6 protons and 6 neutrons. So we give this a mass of 12 units. So these are 12 atomic units. We're talking here at about very small scale. However, 1 mole of carbon atoms weighs 12 grams. So we can scale up. We can scale it up. Now that's a more convenient number to use. So you can use the relative atomic masses from the periodic table, which are in atomic units. So those units that it's in the first bullet point. If you change the unit to grams, that is a 1 mole. So in the periodic table, if you've got helium, it's got relative atomic mass of 4. That means it has more mass of 1 mole of helium is also 4 grams. So something to note down, a summary: 1 mole of a substance contains 6.02 times 10 to the 23rd particles. It's called Avogadro constant. Now, AQA specification says you don't need to memorize the number. It will be given to you in the questions. However, if you want to be a chemist, you better memorize that number. 1 mole of atoms weighs the relative atomic mass in grams, something to remember. We can have a mole of atoms, molecules, ions, electrons, and so on. I will be using it that way in different units in the A-level chemistry. And an amount of moles can be measured out in either grams, decimeter cubic of the solution of known concentration, or decimeter cubic of gas. And we'll look at the application of all these 2 calculations. So if you want to pause and take notes, this is the time. So how can that help us? Okay, so let's work out how much of each substance we need if we had this particular reaction going on. So you can see the equation, when it's balanced, it tells us that 1 atom of carbon reacts with 1 molecule of oxygen, gives us 1 molecule of carbon dioxide. So you can see that it's in proportion, right? It's in proportion. So you've got a certain proportion, right? In this case, it's 1 to 1 to 1. In a different equation, could be 1 to 2 to 3, and so on. Now, if you scale it up, so think of a proportional reasoning. So if you times the number of atoms by Avogadro constant, which is 6.02 times 10 to the 23rd, you get 1 mole of atoms. If you times 1 molecule by the same number, you get 1 mole of molecules. If you times 1 molecule, you get 1 mole of molecules. So you can see this is still in proportion, right? So the number that's in front of atom or molecule, now it stands in front of the mole. So if you times equally both sides of the equation by a number of molecules or atoms in a mole, you can use the balancing numbers from the equation as number of moles. So the same way as you would say 1 atom of carbon plus 1 molecule of oxygen, you could say 1 mole of carbon atoms plus 1 mole of oxygen molecule. However, if you want to turn it into grams, you times the moles by either AR or MR. You learned that in your GCSEs. And the AR or MR will be different for all the different substances, right? So what you end up with, there is no proportion with the masses. The masses are not in proportion, and often people get that mixed up. So moles or number of atoms and molecules are going to be in proportion. So ratio 1 to 1 to 1, or 1 to 2 to 3, and so on. However, once you times it by the masses, it's not in proportion anymore. However, there's a different relationship which doesn't happen with moles. Total of the left-hand side, so 12 plus 32 equals total of the right-hand side, which is 44. This is only true, the green bit, this is only true for masses. This is because of the law of conservation of mass that you learned in GCSEs. This doesn't apply to moles. You can see in here that 1 mole, 1 mole, and 1 mole, when you add up left side is 2 moles and right side is 1 mole. So that law in here, the sum of left-hand side equals sum of right-hand side, only applies to the masses but not to moles. And remember that, don't get that confused. Right, so remember that triangle from your GCSEs. So you need to be able to work out number of moles if you know mass, and if you know the MR, and be able to do all the different calculations around it. A few more details. You need to know that 1 million grams is 1 ton, 1,000 grams is 1 kilogram, and 0.001 gram is 1 milligram. So some examples for you. So pause and have a go, and I'm going to go through the answers. Okay, so let's calculate the number of moles present in 240 kilogram of carbon dioxide. So we need to change the kilograms into grams. So 1 kilogram is 1,000 grams, so you times it by 1,000 to get the grams. Then you find out the MR for carbon dioxide is carbon is 12, oxygen is 16. You times the oxygen by 2, you add it up, you get 44. So if you've got mass, you've got MR, you can work out the moles. Moles is mass divided by MR. Stick the numbers in, you get 5,450 moles. You can turn that into 5.45 kilomole. So kilomole, that means 1,000 moles. So 1 kilomole is 1,000 moles. Okay, now you could have left it like this, but this looks more elegant. And it's 3 significant figures because the data that was given to us, it was 3 significant figures. Okay, so what about the second one? Calculate the mass of substance present in 0.02 moles of aluminium sulfate. So the formula is luckily there for you already. So you can work out the MR of the substance, which is a bit complicated. It's 342.3. You can see here the working out. And we've got the moles. So moles times MR is mass. You work it out 2 significant figures because that's what we had the data in. Next, calculate the relative molecular mass. So that's the MR of a substance. So you're given moles and you're given the mass, and suggest it's possible identity because we don't know what the substance is in here. Okay, so if you need to calculate the molecular mass, you need to know moles and mass. So mass divided by moles, and you get 28. And so what do you think the substance may be? So it's possible that it's N2 because nitrogen is a 14, and that would match. Now the last question, you're more likely to be able to come up with the answer the more if you have more experience. So another lot of examples. So can you pause and have a go? Okay, in this case, in both of these, you need to use the Avogadro's number. If you didn't realize you have to do that, you can pause and have a go. Right, so how do we calculate the number of particles in 5 grams? Well, to work on number of particles, we need to first have moles. So we've got mass is 5 grams. We can work out MR is 207.2 mass and MR. We can work out the moles. Can you see here? I kept the long number, yeah, in here. I didn't round it up yet to significant figures. And then to work out the number of particles, I know the number of moles. I know Avogadro constant, which is the number of particles in 1 mole. I times them, and this is my number. I give it to 2 significant figures because that information was given to 2 significant figures. Now, I did not actually type it into the calculator with this kind of long number. I used the answer function on the calculator, and I showed you here how I did that. So then you need to calculate the mass of this many atoms of magnesium. So we know it's magnesium, so we know that AR for magnesium is 24.3. You can look it up in the periodic table. And then, so you need to know the mass and your given number of atoms. So you need to turn number of atom into moles. And 1 mole is 6.02 times 10 to the 23rd. So how many moles is in here? We need to divide, and we get this number. Now again, I use the answer function on my calculator. And if I were you, I would do this calculation on your calculator, check if you get the exact same number. If not, play around with the brackets, because different calculators have sort of different way of dealing with brackets. Make sure you've got brackets around the correct things. So when you're dividing, your calculator is not messing up your calculation. So then I use the answer function, and moles times AR gives me 24.3 times the answer in here, and this many grams. Now, 10 to the minus 3 is 0.001 gram, and that equals 1 milligram, right? And I had 8.07 of that, so that gives me 8.07 milligram. So further practice for this is task 8, and I will make the mark scheme available. In the next section, we're going to look at variety of calculations related to reacting masses. So this word comes up sometimes, not so much in the questions, but in general conversations around chemistry. So it's good for you to know that word. Stoichiometry. So the stoichiometry means the ratio in which reactants react and the products are produced in simple whole numbers. So basically, it's related to the balanced equation. So if I have a balanced equation where everything is a whole number, that's a stoichiometric relationship. Okay, so for example, 2 moles of hydrogen react with 1 mole of oxygen to form 2 moles of water. That's stoichiometric relationship. So that's what we have in the equations. Now, our equations, as I mentioned before, tell us the ratios. It's proportional relationship. So what is the ratio in this one? The ratio is 1 to 3 to 2. So whether I have molecules or whether I'll have moles, I'm going to have the same ratio. So let's have a look how that works. So if I have molecules, I've got ratio 1 to 3 to 2. If I times it by 12, I need to keep the same ratio, which means the same as a dozen, isn't it? 12 is a dozen. Okay, so the ratio is always going to be 1 to 3 to 2. The same, this is repeated, sorry for that. The same when you have moles. So 1 mole is 6 times 10 to the 23rd of molecules. So if you times it by 3, you get 18. You times it by 2, 2, you get 12. Okay, so I could put 6.02, but it's just to simplify, right? So the ratio is the same. So, but these numbers are long numbers and it's a hassle, so instead we just use moles. So instead of saying 6 times 10 to the 23, 18 times, we just say 3 moles, 1 mole, 2 mole. The ratio is 1 to 3 to 2 all the time. If you have 10 moles, then we have 30 and a 20. The ratio is 1 to 3 to 2. If we have half a mole, then this needs to be times 3, and this needs to be times 2, right? 1.5 times 3 is 1.5, half times 3 is a 1. So that ratio needs to be kept at all times. So what I want you to do is to now pause and have a go at the those 4 questions. Now we're going to go through the answers and the working out for this. So you can see in each of these, the equation is already balanced for you. So you can use the ratio. So in here, the ratio is 4 to 1 to 2. So we're looking at the numbers that are in front of each of the components. So if the ratio is 4 to 1, to get from here to here, I need to divide by 4. So 12 divided by 4 gives me 3 moles. Okay. And then to get to here, the ratio is 1 to 2, so you times it by 2, so that will be 6 moles. We do the same thing because proportional relationship here for 0.1. 0.1 divided by 4 gives you 0.025, and then times 2 gives you 0.05 mole. Okay, in the second example, the ratio is 2 to 3 to 2. So 2 to 2, you can see that is the same as 1 to 1. So you can straight away do this, because from here to here, the ratio is 1 to 1, right? Does that make sense? Okay. Now, to go from 2 to 3, the ratio is 2 to 3, so this one will be a bigger number. So if 2 aluminiums is 3 chlorines, then 1 aluminium is how much? 1.5. So we need to times by 1.5. So how did we work it out? If 2 aluminiums is 3 chlorines, right? So 1 aluminium is how much? You had half it, so it's 1.5. So we do here what times 1.5. So 5 times 1.5 gives you 7.5 mole. And if I do that here, so 0.1 times 1.5 gives you 0.15 mole. So you need to look for these kind of relationships to work that out. Okay, next one. So here we've got the ratio is 1 to 6.5 to 4 to 5. Now, it's always the best if you have one of the components being 1, because then you can just simply do, from here, we're going to go to this one, times 6.5. So from here to here, we'll have times 6.5. From here to here, we'll have times 4. And from here to here, we'll have times 5. So we're not going to go in between each of these terms, we just times as we go. So 0.5 times 6.5 gives me 3.25 mole. Basically, I'm halving it. And 0.5 more times 4 gives me 2 mole. And 0.5 more times 5, half it, 2.5 mole. And the next one, we've got 20 moles. So 20 times 6.5 is going to be 130 mole. If you're in doubt, use your calculator. And 20 times 4 is 80 mole. And 20 times 5 is 100 mole. Okay. And the last one, we've got the ratios 4 to 3 to 2 to 6. So we're kind of going to go a little bit all over the place to make our life easier. So we could go, so I'm looking at the ratios 4 to 3 to 2 to 6. I'm looking at the relationships and I can see where it's the easiest. So from here to here, I could divide by 2, isn't it? From here to here, I can times by 3. And then from here to here, I can divide by 2. So I'm trying to avoid this kind of like weird kind of thing. So I can now work everything out. So let's go in order. 4 to 2, you divide by 2. So 0.5 divided by 2 is 0.25. 10 divided by 2 is 5. Okay. Then from here to here, you times it by 3. 0.25 times 3, 0.75 more. And you times it, 5 times 3 is 15. Okay, and then we take the 6, you divide it by 2, then you end up with a 3, isn't it? So 0.75 divided by 2 is 0.375. Yep. And then 15 divided by 2, that's going to be 7.5 more. I don't want to make a mistake, so I'm just double checking that on my calculator, and you can do that yourself as well. Okay, so remember how these ratios work and try to make your life easy for yourself rather than hard. So next bit, reacting mass calculations. So we're starting to get to some serious stuff now. So we can use balanced chemical equations to find out what mass of chemicals, or volume if we're talking about gases, or volume when we're talking about solutions as well, if we know the concentrations. react or are produced in a chemical reaction. Okay, so this is a typical question. You did that in GCSE, so if this is easy, move on to the practice. If not, then look at me going through the examples. So what mass of hydrogen is needed to react with 40 grams of copper oxide? How would you go about that? Okay, so first of all, this is the method that I suggest so that mistakes are avoided. You need a balanced equation, and you're starting from the balanced equation. You're going to lay out what you already know and what you need to find out. So it says what mass of hydrogen is needed to react with 40 grams of copper oxide. So these are the two things that we told. 40 grams of copper oxide, that is my mass, and hydrogen mass is what we need to work out. Now this also means that copper and water, we don't need to know anything about them. So what I tend to do, so I don't get confused, and like if I can make a mistake, surely you can too. So that I don't get confused, I cross the rest out. It's just, this equation is just there for my working out anyway, yeah? So I can cross it out. Right, so I've got the mass. What else do I know? Well, I know the formulae, so what I can work out is the MRs. So I'm going to work out the MR for copper oxide and for hydrogen, okay, using the periodic table for that. Right, so next, you've got mass, you've got MR. What can we work out? You can work out the moles when you've got mass and MR. So for copper oxide, we can work it out. You use the formula. This is what I got in my calculation. Now here is ratio is 1 to 1. So if I know the moles of copper oxide is 0.503, the mole of hydrogen is going to be the same. If this was a different ratio, then I might need to double it, half it, and so on, like we did in the previous exercise. So now we have the MR and the moles. We can work out the mass is moles times MR, and that's the answer. The answer is now given to two significant figures because our data 40 grams was given to two significant figures. Right, so second question, second example. What mass of iron is produced when 32.0 kilogram of iron 3 oxide is heated with carbon monoxide? So they give you the equation. They tend to give you equation for this one just so that you don't mess it up. Right, so what we can see, and I noticed that first, this is three significant figures. So that means I know down for myself, this exam hint, how many significant figures my final answer is going to be, because I don't need to think about it until I've got my final answer, and I'm not going to round off anything in between. Okay, so what do we know? We know iron oxide is 32.0 kilogram. I can't leave it in kilograms, so I'm going to change it into grams. 32,000 grams. Okay, so what else? What mass of iron is produced? So we don't know that one. Everything else we don't care. There's no information about it. I don't want to get confused. I'm going to leave that there. So this is my mass. Then I can work out the MRs. MR of Fe2O3, if I've got it calculated already, so I don't need to think about it. You can check in the periodic table if I got it right, 159.6, and the AR for the iron is 55.8. Always remember, you only relate your AR to one of the element. You ignore the balancing number, because the balancing number we're going to use in the ratio, not now. Otherwise, you use it twice and you lose a mark. Sometimes you lose 2 marks. It depends. Right, so you've got mass and MR. So if I've got a mass and MR, I can work out the moles in here. So the moles in here is going to be 32,000 grams divided by, right? So divided by 159.6. And that's going to give me 200.5 mole. And then we can see the ratio is 1 to 2. So I need to times it by 2. So I'm going to get 401 mole of iron. So see that 2 was used up here. That's why it can't be used up here. So don't make that mistake. It's a common mistake, but you lose marks. Okay, now we've got the moles and the MR. So my mass is going to be 401 times 55.8, and that's going to give me, if I think back those three significant figures, 22,400 grams. Okay. Now, if you want, because it doesn't tell you what unit, you can put it as 2.4 kilogram. It looks better. Okay. One more question for you to practice. So this one, what amount of oxygen is needed to convert 102 grams of ammonia into nitrogen? Pause if you want, and then we go through it. Right, so first thing, it's three significant figures. So we're going to note it down for ourselves for later. Right, so what mass of oxygen? So that's my question mark. And they give me 102, whoops, 102, I'm writing this. 102 grams of ammonia. I don't care about this, they don't give me any information. Second step, MR, NH3 nitrogen is 1417. And again, you only look at this bit, isn't it? You don't look at the 3 and a 4. And oxygen is 2 times 16 is 32. Okay, you've got mass, you've got R, you can divide and you get your moles. So 102 divided by 17, you get 6 moles. Okay, the ratio is 4:3. So what do you need to do? You need to divide by 4 and times 3, because you need to first see 1 NH3 gives you how many oxygens, and then you times it by 3. So if you divide it by 4 and then times it by 3, you get, just do some calculation, 4.5 mole. Now you've got mole and MR, so you have your, you can work out your mass. It's 32 times 4.5, and that's 144 grams to 3 significant figures. Okay, one more question. This one is the hardest. We didn't have these kind of questions in your GCSEs. So what you can see in here, you've got this situation. So this is a hydrated salt and SnCl2 dot. It could be, for example, 6H2. I don't know how many H2 we need to work out. Okay. Now we could also have anhydrous salt. And this is what we normally talk about. Normally, this is anhydrous salt, SnCl2. But what happens is there's certain salts, so this is a solid, certain salts, when they expose to moisture, they absorb water and they make this kind of bond. We're going to talk about it a little bit more in A level, right? And they attach these water molecules. Now it could be 1, it could be 3, it could be 5, it could be 6, it could be a different number of water molecules. That makes it heavier. Now you can treat this dot as a plus. Okay, so when you're doing calculation, you're just treating it as a plus, as if you added certain number of water molecules into that. Okay, so hopefully that introduction sort of helped. So what do we have? Yeah, oh, this is often also used, actually, one more thing. So when I've got hydrated, for example, copper sulfate, you might have seen this example for reversible reactions. When you heat it up, so this one is blue, solid, and when you heat it up, it loses the water and it becomes anhydrous, and the water would evaporate, right? Turns into gas. So anhydrous copper sulfate, and that is white solid. But when you add water, right, it turns back into blue. So you might have seen this in reversible reactions experiment. Maybe you've done the experiment yourself. So this is a similar thing that happens in here. So you have your hydrated tin chloride and you have 5 grams of this. So this is your mass. and they heat it, and they form 4.20 gram of anhydrous tin chloride, right? And they say calculate the number of molecules of water of crystallization. So this X, what is the X, right? Now this X must be a whole number. So whether you get a whole number at the end, we might need to round off a little bit. You need to have a whole number, and the number is not going to be like 2000. It's going to be a small number. Okay. Right, so how can we go about this? Different ways of going about it. I'm going to show you one of them. ChemSheet's booklet has another method in their booklet that you can see. Let's see if I show you both methods maybe. Right, so what you can work out. So how I like to go about it is to, first of all, that's 4.2 gram. So you can work out the MR of SnCl2, you can calculate it, is 189.7. Okay, so you can divide that and you can get your moles, and that's going to give you 0.02214 moles. Okay, so this is how many moles of the hydrated thing you have. Okay, so what you then can do is you can think of it as an MR. Okay, so you know what, let's do it first the ChemSheets way. Okay, so that's your moles. So that also equals the moles of this, right? 0.02214 moles, right? So that also equals the moles of that, right? So what can you work out? You can work out the MR. Now for this one, the MR would be 0.5 gram divided by 0.02214. So I calculated that, it's 225.8. Right? So you've got your MR. So what now? What now? What do we do now? Okay, so what is the, if I have 1 mole of this, right, so what you do is the MR of SnCl2, right, you have is 189.7, right? So it's 189.7. Yeah. So let me just make it different. So SnCl2 is 189.7. The whole thing is 225.8. So what you can do, you can work out the MR of the X waters. The MR of X waters would be 225.8 minus 189.7. Right, so that's going to be 36.1. So X waters is 36.1, but we know that 1 water, the MR is how much? 16 plus 2, 18. So how many waters get in here? Right, so X equals 36.1 divided by 18. It's about 2. Must be whole number. Yeah, as you remember. Okay, so that's one way of going about this. I'm going to show you a different way, not much different, but a little bit different. Okay, so we have masses. So mass of this one was 5. Mass of this one was 4.2 gram. And then what you can do, you can work out the mass of X water. So that's going to be 0.80 gram. Okay. And then what you can do, you can treat this as well. You need to know the ratio because the ratio is 1 to X. So you can work out the X from this. So what are your MRs? For SnCl2, the MR was 189.7. For water is 18. So then you work out the moles. So 4.2 divided by 189.7 was 0.02214, and 0.8 divided by 18 is 0.0444. right? So this is the ratio, right? But we need a whole number ratio. So we can divide by the smallest. So this is the same procedure as for empirical formula. We will go through empirical formula later if you're not familiar with it. But you should be familiar to some extent from GCSEs, although they don't call it empirical formula in the specification. So we divide by 0.0221 and so on, and you get roughly ratio 1:2, so x equals 2. So this is another way of doing it. Whichever way you do it, doesn't matter as long as you get it right. So further practice for this type of calculation is task 10, reacting mass calculations, and I will make a mark scheme available. Another point that is in GCSEs, but we want you to expand on it, is limiting reagents. Limiting reagent is the reagent that reacts fully, as opposed to the reagent that is in excess, which doesn't fully react. You need to make sure that you know the vocabulary around it and can use it in calculations. Multi-step calculations are all the rage in A-level. So let's have a look. So at start, you have 3 moles of nitrogen and 3 moles of hydrogen. How much ammonia are you going to make? We just need moles, don't need masses. Okay, let's check if you got it right. So first, you see that the ratio is 1:3, right? So 3 moles of nitrogen would need 9 moles of hydrogen for it all to react. But we don't have 9 moles of hydrogen, we don't have enough. So that means 3 moles of nitrogen is not going to happen. Nitrogen is in excess. What that means is that hydrogen is a limiting reagent because all of it reacts, and it's limiting how much nitrogen can react, isn't it? Right? So only 1 mole of nitrogen can react. 1 mole of nitrogen will react, and 3 moles of hydrogen. So 1 mole of nitrogen is going to react. That means we're going to react fully the hydrogen. Right. So ratio is 1:3:2, so that makes 2 moles of ammonia, and that's our answer. So what happened then? You also ended up with 2 moles of nitrogen unreacted, and hydrogen reacted fully. Let's look at another example. I mean, it's the same equation, but different quantities. How much ammonia are you going to make this time? Okay, so ratio is 1:3. So for one, we have 1 mole of nitrogen. We need 3 moles of hydrogen. Do we have that? Yes, we have even more than that. We've got 10. So that means nitrogen is going to react fully, but hydrogen, only 3 will react. Right, so there's more than enough hydrogen. Not all of it will react. Nitrogen is the limiting reagent because it will react fully, and hydrogen is in excess. Only 3 moles of hydrogen can react, so that means 7 moles of hydrogen is going to be left over. So nitrogen 1 mole reacts, hydrogen 3 moles react, and we make 2 moles of ammonia. And we used up all of the nitrogen. We have 7 moles of hydrogen left over, and as I said, we make 2 moles of ammonia. Let's look at one more. Pause. Okay, the ratio is 1:3. So for 12 moles of nitrogen, I would need to have 12 times 3, 36 moles of hydrogen. I don't have enough. So that means nitrogen is not going to react fully. So if I have 24 moles of hydrogen, that will have to then react fully and be the limiting reagent. Okay, so how much nitrogen I'm going to make? 24 divided by 3. 24 divided by 3 is 8. So 12 moles of nitrogen would need 36. There's not enough hydrogen, and hydrogen is limiting reagent, nitrogen is in excess, so you only can react 8 moles of nitrogen. So that means 8 moles of nitrogen will react all of hydrogen, and you make in that ratio, you can work out, probably the easiest is from here to here is 1:2, so you double how much nitrogen reacted. So, and you have 4 moles of nitrogen left over, hydrogen reacted fully, you made 16 moles of ammonia. One more. Okay, so with 10 moles of SO2 would need 5 moles of oxygen. There's more than enough. So that means SO2 reacts fully. It's called limiting reagent. O2 is in excess. So you will fully react all of SO2, but you will only react 5 moles of O2, right? And the ratio from here to here is 2 to 2, which is 1 to 1. So that means I'm going to make 10 moles of SO3. So at the end, you used up all of SO2, you have 3 oxygens left, 3 moles of oxygen left, and you made 10 moles of SO3. Right, so how do we apply that? So this example takes the same idea, but it doesn't ask you that specifically. So you can see what mass of calcium oxide is formed when 10 grams of calcium reacts with 10 grams of oxygen. So when you're given 2 masses, first of all, you need to turn them into moles, but also it doesn't tell you which one reacts fully, which one is in excess. You can't just assume they both react fully. You need to work out which one is in excess, and the one that is a limiting reagent you're going to use for further calculations. So let's have a look. So, oops, sorry. So let's have a look. Right, so what do we have? We have 10 grams of calcium, and we've got 10 grams of oxygen, right? And the mass in here is not worked out. So calcium is 40.1, and oxygen is 32. So to work out the moles, 10 divided by 40.1 gives you 0.2449. Let's keep 3 sig figs. And 10 divided by 32 gives you 0.3125. Okay, so these are the moles. Now the ratio is 2 to 1, right? The ratio is 2 to 1. So if I had 0.249 of calcium, I would have to, ratio is 2 to 1, I would have to half it, and I will have to have 0, 1, 2, 4, 5 reacting. So I definitely have more than enough of oxygen. So this one is my limiting reagent. It will fully react. Okay, so here it's going to be minus 0.249 moles of this. It's going to fully react. So it's at the end you have 0. In here, maybe I should have written that in here. 0. So you react 0.1245. So how much is left over? We don't really need to know, but just to make sure, 0.188 is left over. Okay, but the real question, so this one we don't need to know. We just needed to work it out to see if it's in excess or not. So this one is in excess. Okay, so the one that's in excess, we're not going to use that for the calculation. We're going to use the one that fully reacted. So this one fully reacted, so that we're going to use. And the ratio is 2 to 2, which is the same as 1 to 1, so that's 0.249. And the calcium oxide is 56.1 mR. So mass equals 56.1 times 0.249 equals 13.97. So because it's 3 significant figures, 14.023 significant figures, and that's grams because it's math. Okay. So what you can do for further practice is these 3 tasks and a challenge, and I will make the mark schemes available. In this section, we're going to revise the GCSE's percentage yield and also learn about atom economy, which is not in GCSEs. So percentage yield is the amount of product that a chemical reaction produces. And it's an empirical value. Empirical, that means it needs a practical measurement. So you need to actually measure how much of substance you produce to work out the percentage yield in the actual practical experiment. And the percentage yield tells us about the efficiency of the process. And very few chemical reactions have 100% yield. So there are a few reasons that could be possible. Can you pause and try to come up with as many as you can? So let's see, it could be that the reaction is reversible. It could be that some unexpected products might be formed, so side products. Maybe some of the product is left behind in the apparatus. Right, I highlighted the products because it would be the product, not the reactant. So not enough to say substance. The reactants may not be pure, so maybe you've got impurities. And maybe it's difficult to separate the desired product from the reacted mixture. So for example, if you have a mixture of liquids, you might need to use distillation, may not be 100% efficient. So because maybe the boiling points are really close together. An example of this is water and ethanol. They've got boiling points that are close together, so it's very difficult to have high purity ethanol. So when you're actually doing this in an exam question, then you need to, in GCSEs it was kind of like any of these will go. In A-level, you need to read the question carefully and see which of these will apply. Maybe the reaction is definitely not reversible, because the question makes it clear that it's not reversible, then you can't say the reaction may be reversible. Maybe there's a specific method that's used for separation that is listed in the question, then you can't just say in general, it may be difficult to separate. You need to be specific. You might be talking about maybe some of the product is lost on the filter. So be very specific if the question gives you enough information. Right, so the formula for calculating the yield, you've got percentage yield equals mass of product obtained divided by the maximum theoretical mass of the product. So you need to be able to work out first what is the mass of the product that you're expecting to produce. Okay, so they're asking you in the question, let's look at the example. You've got iron extraction in the blast furnace, and they give you the chemical reaction. And let me just change the ink color. And they say calculate maximum theoretical mass of iron that can be made from 1 ton of iron oxide. So when they're talking about maximum theoretical mass or maximum theoretical yield, it's what we were calculating in the previous sections, which is how much of the product you produce. So we're starting with 1 ton of iron oxide. So 1 ton is, you need to translate that into grams. So 1 ton is 1,000 kilograms. And 1,000 kilograms is 1,000 grams. So 1 ton is 1,000,000 grams. Okay, so we've got iron oxide, and you need to calculate the amount of iron produced. So we know the ratio is 1 to 2. So I could maybe write it like this, and Fe2O3 turns into Fe. So instead of copying the whole reaction, I'm just making it shorter. So I will have 1,000,000 grams of Fe2O3 and question mark grams of Fe. So this is my mass. Now, then I'm going to work out the MRs. So for Fe, the MR is 55.8, and I can work that out from the periodic table. And for Fe2O3 is 159.6. So then here I've got the mass, I've got the MR, I can calculate the moles, because moles is mass divided by MR. So the moles of Fe2O3, if you divide that, you get 6,266 moles. Now from here to here, the ratio is 1 to 2. So to get the moles of Fe, I need to double 6,266. That gives me 530 moles. Okay. Now here I've got moles and I've got the MR, so I can work out the mass. So mass will be moles times MR, and that's going to give me this much, and that is 3 significant figures because here we had 3 significant figures. Okay, so this is normally the first step. They hardly ever just ask you to work out the yield. That would be like a foundation GCSE question, not A-level question. So they're asking you to work out the, so this is maximal theoretical mass of iron. This is if I get exactly 1 ton, so 1,000,000 grams of Fe2O3, ideally, if everything goes absolutely right and none of those factors that we looked at in the previous page work, or happen, this is how much iron you'll get. However, in real life, they got 650,000 grams instead of 699. So they didn't get as much. Now, if you're doing this calculation in an exam question and you end up here with a number that is less than this, you made a mistake, look for a mistake. However, if you're short of time, ignore the fact that you made a mistake, work out the percentage yield, which may not make sense, but you only lose some marks here for processing, and here will be error carried forward. ECF, that's often written, so that's error carried forward. So 2 points again. These numbers, you need to make sure that this one is smaller and this one is larger, because your expected amount is your maximum amount that you can get. You can't get more than that. However, so this number is smaller. However, if you're short of time, instead of panicking and looking for an error, you're going to ignore if you got the wrong answer, and you're going to still move on to calculating your percentage yield. If you have the time, you can always go back and look for the error. Why? Because you've got this thing error carried forward. That means if you run out of time and don't calculate this, you're going to lose the marks for calculating percentage yield. But if you had an error in part A, but you use that incorrect answer to work out part B, you'll still get processing marks, and this will be marked as error carried forward in your in your marking. Okay. So how do we calculate percentage yield? So percentage yield would be equal, you have mass of product obtained, so that's how much they made. So they made 650,000 grams, and you divide it by how much we were supposed to get, okay, and times 100 to get a percentage. So if you stick that into the calculator to 3 significant figures, you're going to get 93.0%. So that's 3 significant figures, because again, this is the value that we have. Now, the thing is, this number in here, we don't know how many significant figures, but it's minimum 2 significant figures, because we don't know if those zeros after, are they significant or are they not significant when you are showing the the numbers in that way. Okay, so further practice for this one is task 12, percentage yield. And moving on to atom economy. So atom economy sometimes get confused with the percentage yield. It is used to assess how much of the starting materials end up in a desired product and how much is wasted. So the higher the atom economy, the less waste is produced. So what atom economy is used for, it's a theoretical calculation. So it's not based on the practical, and it's found directly from the balanced equation. So if I have 2 different processes to produce the same product, and they have 2 different chemical reactions that is represented by 2 different balanced equations, I can do a theoretical calculation to see which of these processes give me less waste and more product. Okay, so let's look at some examples. So this is your calculation. So to calculate atom economy, you divide mass of the wanted product, which is, read the question carefully. In the question, they will tell you which of the products is a wanted product, and divided by total mass of products from the equation, or total mass of reactants, because you remember the mass of products equals the mass of reactants in a chemical balanced reaction. The reason is law of conservation of mass, right? So let's have a look at this example. So you want to know this process is fermentation. Fermentation, you make ethanol. That is your wanted product. Carbon dioxide is your waste product, right? So you don't do this process of fermentation to produce carbon dioxide that goes to the atmosphere and contributes to global warming. You do it to produce alcohol, ethanol. Okay. So how do we go about it? So what you can do is you use the ARs. So carbon is 12, hydrogen is 1, oxygen is 16, and you will have carbon, oxygen, hydrogen in there. And you work out all the substances. Now, in this particular case, this is where it's important. Can you see I include the balancing numbers? So I want to see if I take the molar quantities that are listed in here, so 1 mole of glucose, 2 mole of ethanol, and 2 mole of carbon dioxide, what numbers am I going to get? Okay, so let's start with the mass of the wanted product. So what I'm going to do the MR of ethanol, right? And I'm going to times it by 2. So I'm going to have 2 carbons, 1 oxygen. That's 2 times 12 plus 16. And then I'm going to have 6 hydrogens on top of that, times it by 2. I calculate on the calculator, and that ends up being 92 grams. So make sure you include, in atom economy, you include the balancing numbers in your calculation. Okay, and if I do the same for carbon dioxide, 1 carbon dioxide is 44, so 2 carbon dioxide is 88. So I calculate my molar quantities, so we presume we have 1 mole, 2 mole, and 2 mole, turn it into grams. Yeah, turn it into grams. Okay, so if you see, when you add that together, you're going to have 180 grams of products. And if you checked and worked out for glucose on the left side, you have 180 grams as well. Why? Because law of conservation of mass says the mass before the reaction needs to be equal to the total mass after the reaction. Okay, so that's what I meant in here, that it doesn't matter if you use total product or total reactants as long as it's the total mass, because it should end up the same. Sometimes it depends on the reaction. Some reactions easier to do one way or the other. It really depends. Right, so how do we calculate our atom economy? Our wanted product was the ethanol, and we worked out that's 92 grams. So if I take 180 grams of the product, of my reactant, sorry, my glucose, I make 92 grams of ethanol. And I took 180 grams of my reactant. Okay, times 100, you get 51%. So what does that mean? Out of my 180 grams, I can show it a bit like, you know, those arrows in energy, the Sankey diagrams, energy Sankey diagrams for physics. Let's show it like this. So when I have 180 grams of the glucose, right, about half of that, so 51% of that is going to make 51% of that is going to, so that's my 100%. 51% of that is going to make my ethanol, which is my product, and 49% is waste, right, which is my CO2, right, and this is my wanted product. So what that means, if I'm a manufacturer and I just spend money on that 180 grams of glucose, and half of that money is going down the drain as waste, I'm not going to be very happy, isn't it? Okay, so what I'm going to do, I'm going to look for, maybe there's a better process, isn't it? Maybe there's another process that's going to help me. In this case, actually, there's a process that makes ethanol from crude oil that is better in terms of atom economy, is less wasteful. However, it has implications in terms of the environmental factors. Okay, so manufacturers should look at all the different factors together, not just a single one. Right, let's look at another example. So we've got sodium chlorate, which is an ingredient in household bleach. Okay, so find the percentage atom economy in the reaction. So let's look at the reaction. So the reaction is given for you. So how do you go about it? Pause, have a go, and then we're going to check. So let's check. It says find the percentage atom economy of sodium chloride. So which one is sodium chlorate? It's NaOCl, that one here. That's your sodium chlorate. How do we know it's the chlorate? Because that one is a chloride. Do you remember chloride? Ide is the one without oxygen. And this one is chlorate. Okay, if you see oxygen, it's 8. If you don't see oxygen, it's ide. So if you did it for the chloride instead, so pause and have a go and fix it. Right, let's go through the answers. So mass of the desired product, sodium is 23, oxygen is 16, chlorine is 35.5, so you get 74.5 gram, right, if we assumed molar quantities. Okay, then the total mass of reactants. So what I did the reactants because it's shorter. I could have added all these together, it doesn't really matter. So I got 151. And then you divide them. Okay, and that gives you 49.3. So that means 50.7% is wasted. Right, so one more point that they want you to consider in the specification is economic, ethical, environmental advantages for society and for industry developing chemical processes with high atom economy. And I kind of mentioned that a little bit, but let's look at that in a bit more detail. And credits to the...
Next, we need to cover the main reasons why it's important to consider atom economy. Number one is that raw materials are expensive. And so if they're mostly being converted into waste products, the process is generally going to be less profitable. Reason two is that it's less sustainable to use large quantities of reactants to make tiny amounts of products. And three, waste products themselves can be expensive to get rid of and can damage the environment. The best solutions to these problems are to either use a more efficient reaction or to find a use for the waste products so that they become useful byproducts instead of waste. And even if they can't sell these useful byproducts for very much money, it's still much better than paying to dispose of the waste. The last thing to cover are that there are lots of other important factors to consider when you're thinking about how profitable a reaction is. For example, the percentage yield, the cost of the raw materials, the position of the equilibrium, the rate of reaction, and the cost of maintaining the right conditions, like the temperature and the pressure. Anyways, that's everything for today. So if you found it useful, then please do give us a like and subscribe, and hopefully we'll see you again soon.
Right, so credits to this channel. If you want to watch that video, you can find the link in here. So further practice for this topic is task 13, atom economy, and I will make answers to this one and the yield one available. So now in your booklet, this is the last section, but it kind of fits into the theme of moles and mass better than what's the sections in between. So you can jump into the booklet in the last section called Empirical and Molecular Formula. We're going to cover that now. So what is an empirical formula? Empirical formula is the simplest ratio of atoms in a compound. You can see here silicon dioxide. What type of structure is silicon dioxide? For silicon dioxide, you should know it's a giant covalent structure or macromolecular. So it's not a molecule. So as I mentioned before in the first video of this amount of substance, in silicon dioxide, this is the formula SiO2 is not showing me that it's one silicon and two oxygen atoms making a molecule. It tells us instead that the ratio of silicon to oxygen is 1 to 2, but the actual total numbers, it's a macromolecule, it's not a molecule, right? So the actual total numbers is going to be huge. The same idea for ionic. So this was giant covalent, right? This is what happens in giant covalent. And this one is for ionic. So for ionic substances, like in here, sodium chloride, you will have formulas NaCl. That doesn't mean it's one sodium and one chloride connected together. That means in the crystal, in the lattice, right? So this is a lattice, and the previous one was a lattice as well. So in the lattice, the ratio of sodiums to chloride is going to be 1 to 1. So all substances have an empirical formula, and the definition to memorize is empirical formula is the simplest ratio of atoms or ions of each element in a substance. And for most substances, it is the only formula. So the substances that are made of molecules often have molecular formula, but other substances like that are not simple molecular, so everything that is not simple molecular, empirical formula is the only formula. Molecular formula is only for simple molecular substances. And molecular formula gives the actual number of atoms of each element in one molecule of the compound. You need to know that definition as well. These two, they come up as definitions, empirical formula and molecular formula as definitions for 1 mark questions. So this is water, right? So for water, water is simple molecular structure. So it's not a lattice, it's molecules. So in water is H2O. So the ratio, empirical formula is H2O, and molecular formula is H2O, right? So the empirical formula shows me that ratio of hydrogens to oxygens 2 to 1. And molecular formula shows me that in one molecule I've got 2 hydrogen atoms and 1 oxygen atom. So this is oxygen atom, it's not O as in like 0. It doesn't say 10. Another example, benzene, right? So you can see the black ones are carbons and the white ones are hydrogens. So you can see if you count the blobs, there's 6 black ones, so there's 6 carbons. And the smaller white ones, they are hydrogens. You can see 5 of them, but there's a 6th one at the back. So each of the black blobs have 1 white blob connected to it. So that means the molecular formula is C6H6. Each molecule has 6 carbons and 6 hydrogens, right? However, the ratio is 1 to 1 because it's 6 to 6. You can simplify that to 1 to 1. So the simplest ratio is 1 to 1 of carbon to hydrogen. That means empirical formula of this benzene is CH. However, each molecule is not made out of 1 carbon, 1 hydrogen. It's made out of 6 hydrogens, 6 carbons. So molecular formula is C6H6. So how do we find an empirical formula? You need to know the mass for each element in the compound. And so how does it work? So for example, they might tell you the percentage. Normally what they tell you, they say, okay, compound is made out of carbon and hydrogen. And they say, okay, there is this much percentage of carbon by mass and this much percentage of hydrogen by mass. Or they might tell you there's this many grams of this or grams of hydrogen. Now, once you've got these numbers, then you have to divide them by the either AR or MR, by the AR of each element. And then this will give you the moles. And then what happens when you've got molar ratio, so let's say you end up with 1.1, 2, 3, 3. Then you need to find the simplest ratio. So this is not yet the simplest ratio because 1.1 mole to 3.3. You could divide both of them by the smallest number. So your smallest number here is 1.1. So you end up with ratio 1 to 3, right? Because that's the simplest ratio and it's the whole number ratio as well, right? And then you put the numbers back into formula. So for example, it would be CH3. Yeah, this is just kind of like a rough example. I'm going to show you a specific example in a second. Okay, so let's look at this one. So we've got if 9 grams of aluminium reacts with 35.5 grams of chlorine, what is the empirical formula of the compound formed? Okay, so how are we going to go about it? I'm going to take you through the method, and then I'm going to do the calculation for you. Okay, so let's have a look. Oops. So you've got, first you're going to put symbols of elements. So we've got aluminium and chlorine, we're going to put Al and Cl. Then what you're going to do is write underneath each of the elements the mass in grams. And if the mass in grams is not given, you're going to put percentages as if it was grams, just assuming percentages in grams. Then underneath you write the AR of each element. You divide mass by AR. You find, so that will give you the moles, and then you find the simplest ratio, and there are some methods to do that, and then you put the numbers back into the formula. So let's have a look what that would look like for this particular work here. I need to get my calculator, okay, because I haven't got the answers for this one. I'm just freestyling it. Whoops. Okay, so we're going to first write the two symbols. So we've got Al and Cl, and then mass of each element underneath. So they said we've got 9 grams of this. I don't know what my 9 looks like, a G. Okay, and then 35.5 gram of Cl. So then we have our ARs we put underneath, which is 27 for this guy and 35.5 for that guy, right? And then we divide them. So that gives you, so this is your mass, this is your AR, and then you get your moles, right? So 9 divided by 27 is going to give you 0.3 recurring, and then the Cl is going to give you 35.5 divided by 35.5. Now, so you can find the simplest ratio by dividing or by the smallest number. So I'm going to divide by 0.3 because it's the smaller of the two numbers. So that's divided by 0.3 will give me 1. That divided by 0.3, it's a recurring, that will give me 3. So my ratio is 1 to 3. But I can't forget the number 6, which is to put the numbers back into the formula. So my AL is 1, and then CL is 3, and this is my final answer. So this is the working out for this particular work. Okay, so if I know the empirical formula and if I know the MR, I can work out the molecular formula. So you'll need to be given two things. You need to be given empirical formula and MR. If I have those two, I can work out the molecular formula in here. Okay, how am I going to do that? I'm going to take the molecular formula, yeah, and times it by MR and divide it by the MR of the empirical formula. So what does that mean? MR of the empirical formula is 14, right? 1 carbon is 12 and 2 hydrogens is 2, that's 14. So I'm basically seeing how many times in the MR the empirical formula fits, right? So if you divide 56 by 14, you get 4. That means CH2, which is the empirical formula, fits 4 times into the molecular formula. So molecular formula must be C4H8. Right, so hopefully that makes sense. Right, So I'll do a couple more examples, one with empirical formula and one with molecular as well. Yeah, so that you can see a little bit, you can see a little bit better. So a compound is found to contain by mass this much iron and this much oxygen. So I'm going to put Fe and I'm going to put O. And they give me percentages, not masses. However, I'm going to assume that this is grams. Okay, so this is my grams. Right, then I'm going to divide by the AR. For iron it will be 56, for oxygen is 16, and I divide them to get the molar ratio. I'm going to get 129. I've got this calculated before, so I can very simply just put the numbers in. Now, so what that gives me is the two numbers that I don't know what's the ratio. So if you see numbers like this, don't round off. Okay, it's often people do that, and that's a mistake. You can only round off when it's like 1.99. Well, fair enough, right? 1.96, fair enough. But you're not going to round this one off. You're going to divide both of them by the smaller number, which is the 129. And in here, you're going to get 1. In here, you're going to get 134. So so first I divide by the smallest. Right, I still haven't got whole numbers, and this is too big to round off. Yeah, it's too far off from 1. So what I'm going to do now, I'm going to times this to see if that's going to help me, okay? So if one of the numbers is 1, just dividing by the smallest, again, is not going to work. So you can't divide, because divided by 1 is just going to give you the same thing, yeah? So you can't divide by 1. I mean, you can, it's just not going to give you anything. So what we do, we check times 2, times 3, and so on, and see which one works. Now I can see already here that it's the ending in here is 3, 4, so it's similar to 3, 3, 3, 3, 3, 3. So times 3 should work. So if I times it by 3, I get 3 in here, and 134 times 3 gives me 4.02. This is good enough to round it off. Because this is second decimal point, so I can round it off. So the ratio is 3 to 4. So then you need to remember what is the empirical formula. That's not a formula yet. You need to write Fe3O4, and that is your empirical formula in here. Hopefully that makes sense. Another example. So you've got 0.25 gram of hydrogen reacts with oxygen to produce 4.25 gram of hydrogen peroxide. Okay. And MR is given, and because you need to work out the molecular formula eventually. So what do we have? We've got hydrogen, we've got oxygen. Hydrogen is 0.25 gram. How much oxygen? They didn't tell you, but they told you the total. The total is 4.25 gram minus 0.25, which is the hydrogen. That means oxygen is 4 grams. Okay. The ARs for hydrogen is 1, for oxygen is 16. So 0.25 divided by 1 is 0.25. So this is my moles here. And 4 divided by 16 is a quarter. So you're going to have 0.25. Super easy. These two numbers already look like each other. So the ratio is 1 to 1. Right. So formally what you did, we divided by 0.25, isn't it? Both numbers. The ratio is 1 to 1. Now, so what's the empirical formula? It's HO, right? Now, so what's the molecular formula? How do we work it out? So we need to take our empirical formula. So molecular formula is our empirical formula, and we take the MR, which is 34.0, and you divide it by MR of empirical formula. So this is 1, this is 16, so that will be 17. So this is MR of empirical formula. Okay, so, and this is times. So that's HO times, it needs to be a whole number. This must be a whole number. 34 divided by 17 is 2. If you've got like 2.02, you just round it down. And what that gives me is H2O2, which is my molecular formula, and we sorted. So some methods of simplifying, you can only round up and down if the number is very close to a whole number. Like, for example, 402 will be 4, but 4.3 is not going to be 4. Don't round it like this. Yeah, so that's fine. That's not good. Okay, so the divide by the smallest. And if the smallest is 1, try multiplying by 2 or 3, etc., until it works. And the further practice for this unit, for the empirical and molecular formula, is task 18, and I will make the answers